When you submit a sensitive request, like a funds transfer or a password change, modern web applications protect that action using a CSRF token. This is a unique, cryptographically secure value exchanged between the client and the server to validate the request. The engineering assumption here is straightforward. Because an external attacker cannot predict or forge this cryptographic token, the state-changing request is entirely safe from manipulation. Yet, unauthorized funds transfers continue to occur on platforms that have perfectly implemented CSRF validation. An attacker can drain an account, and the server's logs will show that the transaction was executed with a perfectly valid, mathematically sound cryptographic token. This paradox exists because the attack bypasses request forgery entirely. Instead, the exploit works by decoupling the user's visual intent from their actual mechanical input. This diagram highlights the different attack vectors. On the left, traditional cross-site request forgery tricks the browser into forging a background request. On the right, UI redressing, or clickjacking. Here, the request is manually, physically executed by the legitimate user. Because the user is operating within a valid session and physically generating the click event, the browser treats the execution as highly trusted. UI redressing cannot be stopped by request validation algorithms, like CSRF tokens. Securing the endpoint requires enforcing strict server-side iframe embedding policies. To see how this exploit is built, we can map the browser's document object model layer by layer. The attacker starts with a blank DOM, establishing a baseline layer at z-index 1. This layer hosts an attractive decoy interface, perhaps a button offering a prize. Next, they inject a secondary layer into the DOM, loading the target website into a cross-origin iframe. Using CSS position absolute, the attacker aligns the target application's action button exactly over the decoy button. By setting this iframe to z-index 2, it sits on a higher spatial plane. It will now physically intercept the cursor's interaction before the click can reach the decoy layer. To hide the trap, the attacker manipulates the CSS opacity parameter. Dialing the target layer's opacity down renders the iframe completely invisible to the human eye, without removing its physical geometry from the DOM. Attackers often use a microscopic opacity value, like 0.00001, rather than absolute zero. This actively circumvents threshold-based transparency detection algorithms present in some modern web browsers. The DOM is now weaponized. The user visually perceives the decoy button, but they will mechanically interface with the hidden target application. When the user attempts to interact with the visible decoy interface, their cursor strikes the invisible iframe. The browser detects a valid click on a recognized domain. It responds automatically by appending the user's valid session cookies to the outbound request. Because the iframe loaded the legitimate target application directly from the source server, the form inherently contains a valid, newly generated CSRF token. The browser dispatches the request. The server checks the session cookies. It validates the CSRF token. Every cryptographic check passes. CSRF tokens are blind to the UI context. They fail against clickjacking because they authenticate the origin of a request, not the human intent. Historically, developers attempted to mitigate iframe exploits using client-side frame-busting JavaScript. These scripts run in the browser and verify if the target page is the top window, enforcing rules like top.location equals self.location. Attackers neutralize this defense using structural countermeasures. They wrap the target iframe payload inside an HTML5 sandbox attribute, creating a highly restrictive environment around the target application. Within this sandbox, the attacker applies the allow forms and allow scripts values. This ensures the target application can still process the stolen click and execute the transaction. The critical vulnerability relies on a single omission. The attacker intentionally leaves out the allow top navigation parameter from the sandbox rules. When the target site's script attempts to break out of the iframe, the browser's security model actively suppresses it to enforce the sandbox restrictions. Relying on DOM-based client-side scripts for defense is an inherently flawed strategy. The attacker completely controls the rendering environment containing those scripts. Attackers continue to evolve UI redressing beyond static overlays. Exploits like double clickjacking manipulate rapid context switching. The attacker tricks the user into double-clicking, dynamically swapping the underlying page between the first and second click to align sensitive buttons with the cursor. Other methods utilize CSS and SVG filters as logic gates to process and leak cross-origin pixel data, extracting sensitive information from the iframe without requiring JavaScript at all. If the target application is rendered by a hostile client, attackers will find new timing mechanisms and rendering side channels to exploit. Because CSS opacity can be manipulated and JavaScript can be sandboxed, defense must occur at the network layer before the browser even attempts to construct the DOM. This requires configuring the HTTP response header. The legacy approach uses the X-frame options header. A server can issue a deny directive to block all framing globally, or a same origin directive to restrict framing to internal architecture. While X-frame options is effective, it suffers from inconsistent browser implementation and lacks the granular control required by complex, modern application architectures. Mitigating modern UI redressing requires a standardized, universally enforced directive that supersedes the DOM entirely. The modern standard is the Content Security Policy, specifically the Frame Ancestors Directive. Declaring Frame Ancestors None or Frame Ancestors Self establishes an overarching, non-negotiable rule set directly by the server. When the browser receives this CSP header, it will outright refuse to render the content inside any unauthorized iframe. The attacker's CSS opacity values and HTML5 sandbox configurations become mathematically irrelevant because the browser drops the payload before it renders. True endpoint security requires a dual approach. You must validate the cryptography of the request using CSRF tokens while strictly governing the rendering context via Content Security Policy. This ensures the user's intent always matches their mechanical action.